So now I guess I have to do some work. I'll talk about mechanism design with evidence, and this is based on joint work with Eddie and Bart. Okay, so yesterday Eddie talked with you about evidence in games and principal agent models, and today I'm going to talk about evidence in mechanism design with multiple agents. Most of the talk is based on a paper with Bart and Eddie, the first paper, but I'll also talk a bit about a different model which turns out to be related in an interesting way, although it does not have evidence per se. It turns out that it's related in an interesting way to models with evidence, which is something we discovered only when we worked on the current paper. Okay, maybe I should say, I think Eddie did a great job in motivating the interest in looking at models with evidence. But let me add a few more words. I think it's fair to say that if you look at the literature on mechanism design, which is vast, then most of it the focus of most of it is on the role of monetary incentives in having types reveal themselves and make it possible for the principal to implement an objective that fits his interests. Okay, so if you remember the opening talk by Eric, the classical models of public goods and allocation of a single unit, which is, by the way, most of this talk will be about that problem in the context of evidence. So there, the monetary transfers play a major role. But there are, Eddie mentioned many examples, I'll mention a few more. There are many problems of economic interest, especially in organizational economics, public economics, and political economics, where monetary transfers play a very limited role, if at all. By the way, it's an interesting question why that is the case. Okay, I don't think we have a good theory about that. But if we simply look at reality, what we see is that in many such cases, and I'll mention a few examples soon, the key role in determining what can actually be implemented is played by evidence, by the kind of evidence that agents can put forward. And in a moment, I'll give you a few examples of the kind of situations we're thinking about. Now, most of the work on evidence, as you saw in the talk of Eddie, considers games or principal agent models, and there's very little, as far as I know, that has been done on mechanism design with evidence when there are multiple agents. So I'm sure there are other papers, but what I'm aware of is the short list that you see on the board. And I don't want to dwell on it. I'll just say that those papers deal with implementation in the context of complete information. That is, in a situation where all the agents know the state of the world, while today we'll be talking on what is the major focus of mechanism design, namely a situation where an agent knows his type but does not know the type of other agents. Okay, so here are a few examples. In a moment, I'll define the formal problem that includes all of those. One setup you might want to think about is a manager who wants to hire a new employee for a job. There's some candidates. The terms of the jobs are fixed. Let's say it's a job in the public sector. And basically, the decision is going to be made by the kind of evidence that the agent can bring about their experience, their competence, and so forth. Okay? Each one of them is interested in the job. The manager would like to hire the one who would be most competent in doing it. A slightly more, not slightly, but a similar but more involved situation or richer situation is something we are familiar with in the context of the university, where you have a situation where the dean, say, of social sciences has a job slot to allocate, and then each department would try to push for its candidate. Okay? It's a situation that's a bit more richer than the first one, because a job in the economics department is not the same as a job in the sociology department. You have different qualifications you need from the candidates, and also it's a different kind of job. And you want to take into considerations not only the competence of the candidates, but also the needs of the departments and so forth. So it's a more involved situation. But anyhow, the basic problem is similar. There's a jobs, you have to allocate a job slot, and you would do that on the basis of the kind of evidence that each department brings about its candidate, about its needs, and so forth.
There is no money at all, only
what?
evidence?
Okay, so in a moment I'll define precisely the problem we're looking at. Yes, the talk here would assume that there's no money. Okay, of course the next step, okay, is to enrich the model by allowing also for monetary transfers. Okay, but this is something that I don't think has been done so forth. Okay. So here's the third example is an example from the public sector. A government is interested in building a big public project, say a hospital, and has to decide about the location, namely about the town. There's a certain set of possible towns, and in such a situation, usually each mayor would try to present evidence to the government that it's the best thing to build a hospital in his area. Okay? Okay, so all these examples fit into what I'll discuss today. We have some extensions which I'll mention, but because time is limited, I'll just talk about what we call the simple allocation problem. So a principal has one unit of an indivisible good, but as you saw from the example, one could think about this good in different ways, like a job slot. The value for the principal from allocating the good to agent I is private information of agent I. Okay? Now, there might be cases, like in the talk of Eric, where the value for the principal is simply the utility that the agent derives from the good. But in many cases, like in the hiring example, that's not the main concern of the principal. He wants to know the competence of this. So the private information of the agent would be his competence or other features that are relevant for the performance of the job. Now, the new element is that we have no monetary transfers, but the tool that the principal has is the fact that agents can prove some facts about themselves. So an agent would be characterized by what we call an evidence technology, which is something that Eddie described to you, and in a moment we'll remind it and be formal about it. But right now the agent is simply can prove some facts about himself. And now we're looking at a situation where each agent wants the good regardless of his type. So let me mention we will focus on the problem I just described to you, but the results, which I'll tell you about in a moment, apply to several interesting extensions. First, we can extend that to the case where there are multiple units. So say the dean has several slots that he can allocate. You can think of also of multiple units as many small units where the problem sounds like allocation of a budget, okay, where money is finitely divisible. We can also extend to the case where some types of each agent want the good and others don't. What is a problem to which that could be of interest? Say a problem of allocating a task. Okay, so a task comes both with burdens and with benefits. And some types of a given agent might, the benefits outweigh the burdens, and for some other types, it's the other way around. For the case where the principal has just two actions, namely just two alternatives that he has to choose from, say whether to provide a public project or not, where the way this public project is funded is predetermined, the results that we have are completely general. Okay, so you could think, you know, each agent characterized by the value that he assigns to this public project, and then some types of a given agent might want the project because the value is higher than the cost, some types might not. And of course, this could vary among the different agents. So the results I'll be telling you about apply to this context as well. But after mentioning this, I just want you to think from now on the simple allocation problem. Okay, so what are the main results? We actually know already from the work. I mean, ideally, what would we like? Ideally, we would like to characterize the optimal mechanism as a function of the parameters of the problem, right? But we already know, actually, from the work that has been done, and Eddie mentioned yesterday, the work by Glaser and Rubinstein and Scher and Hart, Kremer, and Perry. We actually know that there's not going to be any simple characterization of the optimal mechanism without further assumptions, without some, you know, rather strong assumptions on the kind of, on the economy, namely both on the preferences and on the evidence technology, okay? And so what the general results that we could obtain are that there is an optimal mechanism that has three attractive properties. Of course, under certain conditions which apply for the allocation problem and apply to the examples that I mentioned. So the mechanism is deterministic, and it satisfies what we call robust incentive compatibility. That is, and I think that from an economic point of view, this is the most important result, because what it says is that truthful revelation of type and presentation of maximal evidence, there is an optimal mechanism where truthful report of type and presentation of all evidence is the best thing the agent can do, no matter what the other agents are doing. Okay, good. Turns out that when you have type-dependent messages, this notion of robust incentive compatibility that I will soon define is actually stronger both than ex post incentive compatibility and then weakly dominated strategies. I'll give a simple example. And the reason is that you have a situation where messages are type dependent because evidence varies with types. But conceptually, it's the same thing, okay? Conceptually, it's the same thing. You don't need to worry about what other agents are doing, okay? The third result, which is similar to results that Eddie mentioned in the papers, again, by Glaser, Rubinstein, Scher, and Hart, Kremer, and Perry, is that the outcome of the mechanism, although the proof is different, we could not adjust their proof to prove this result in this context. So the outcome of the mechanism actually can be implemented even when the principal cannot pre-commit, okay? So he just responds optimally ex post. Okay. Furthermore, one can show that the equilibrium strategy of each agent in the multi-agent game, where they send reports and the principal acts, is actually an equilibrium strategy in a disclosure game of the type that Eddie described to you, where the principal has a quadratic loss function. I'll remind you all that soon. So his equilibrium strategy in the multi-agent game without commitment is actually an equilibrium strategy of a disclosure game between him and the principal, where he's trying to convince the principal that he has a high value, and the principal tries to match his value. I'll of course be more formal about all this. Okay. Now, one implication of this last result, which I'll show you, is that we can compute the optimal mechanism by solving, in some cases, of course, in some cases, it's convenient to compute the optimal mechanism by solving these single agent disclosure games. Okay. In particular, in the die evidence model, there is essentially a unique strategy for the agent in the single agent game with the principal, and therefore that allows us to quickly solve for the optimal mechanism outcome in the multi-agent setup. Okay, so what do I hope to do is listed here. And let's get started. Okay, so formally, what is the simple allocation problem? It's defined by the parameters you see here. There's a set of agents. The model is finite. Okay, so each agent has a finite set of types. There's a probability distribution on the set of types of each agent. The types are independent. Yes, the distribution is known. A type defines two things. It defines the value first. The real parameter, namely the value for the principal from allocating the good to that type. By the way, we assume that the principal has the option of, and we just normalize, of keeping the good and just normalize it to be 0. This is not essential. And every agent wants the good regardless of his type, okay? Going back to what is a type, so a type defines first how much it's worth for the principal to give the good to that type, and then also the kind of evidence that type can present. Now, the model of evidence is the one that's been used in the literature and that Eddie described to you yesterday. It's the same model. You have a set. Let me just go over it quickly to remind you. You have a set of what we call hard evidence messages, and what makes a message a hard evidence message is that it can be sent by just some of the types, okay? So what is sometimes called the evidence technology is a function that associates with each type some subset of hard evidence messages, okay? And when an agent presents a hard evidence message MI, then what is he proving? He's proving do I have this? No, I don't think I have it. He's proving to the principal that he belongs to the set of types who can present that evidence. This is just like it was in the talk of Eddie. Now we make the assumption of a normality, which I think Eddie criticized too harshly. I mean, there are situations where an agent can present all the evidence that he has, although there are interesting situations where that's not the case. In any case, a complete and rich model would have a cost for each type of evidence that is presented. So in any case, we have to abstract from those. So we make the assumption of normality to get the revelation principle, which I'll remind you later on, and that you don't even worry. You don't need to worry about the formal definition. It basically says that the agent has a message that proves all the things that he can prove. In short, he can present all the evidence that he has. Okay?
That he can uniquely identify type?
No. This simply says that he can prove everything that he can prove by single message. He can. There's a message that gives the evidence that would be conveyed by all his messages put together. Qualitatively, that simply means that he is free to prove anything that he can prove.
So if the system he can send the set of messages and then it's automatically.
What? It doesn't mean that he can prove who he is.
No, okay, but can he send, if he can send more than one message, he can just send all messages and then.
Well, formally, I don't want to get into the exact formality, okay? Because there is a message that proves. What this says is that there is one message that proves the event, that is the intersection of the events that are proved by each one of the single messages. Okay, that's the formality.
But it does not say that the agent can send two messages at a time.
No, formally he sends one message. Okay, let me go on. Okay, because this is I mean on the qualitative level, this simply means he can prove anything that he can. He can present all his evidence. And now sometimes it would be convenient for us to identify the hard evidence message, which is something a bit abstract, with the event that it proves. Okay, so sometimes I will just write the hard evidence message as the event that it proves. So in particular, the Dye evidence model, this is a more general formulation than Dye originally gave. Basically, it's a situation where some types cannot prove anything, okay? So the event they are proving is that they are simply agent I. So you see I'm identifying here between the hard message and the event that is being proved. And some other types can, of course, either not prove anything, but also have the possibility of proving exactly who they are. Okay. Now, what's a mechanism? Okay. A mechanism associates with a profile of types and a profile of pieces of evidence, a probability distribution on the set of agents, namely, with which probability will each one of them get the good. Okay? And the revelation principle, which Eddie talked about yesterday and which applies under the assumption of normality, says that we can restrict attention to mechanisms where an equilibrium strategy is to truthfully report your type and present all the evidence that you have. Okay? Now, we suspect that we can weaken. We don't, but we were simply not so much interested in exploring. We wanted to go ahead with the revelation principle, and we're less interested in exploring whether you could weaken the assumptions and still get the results, although that's something interesting to do. Okay. So, given such a direct revelation mechanism, we can really look at its outcome as really defining it. Namely, we can simply think about it as a function that associates with each profile of types a probability distribution over the set of agents, which specifies with, again, the probability with each one of them getting the good. Now, to look at the incentive constraints, we of course want to look at the interim, what's called sometimes the interim probability, namely, when I'm type Ti, what is my expected probability of getting the good before I know the types of the other people.
He already knows his type, right? You say the last line ex ante.
Yeah, the ex ante or the interim. Yeah, maybe I shouldn't say ex ante, but the interim rather. I don't know. I mean, what is my, what? Well, you know, the formal definition is here. It's the expected probability that you will get the good. Okay. What do you think would be your probability of getting the good when you know only your type, and you're going to play the mechanism? So the mechanism has not been played yet. Okay, what's the optimization problem in this case? Well, this is the objective of the principle, right? This is how much he's doing if on agent I, if the type of agent I is Ti. So we take an expectation for each agent, giving the expected benefit that the principle derives from only that agent, and then you sum over all the agents. And the incentive constraints here are very simple. It should be the case that type Ti gets the good with a probability that is greater or equal than any other type that he could imitate. Okay? The types that he could imitate are exactly those types who have a set of messages that is included in his set of messages. Okay?
Can you explain it more?
Yes. Type, you have to make sure that type Ti gets a payoff, which in this case is simply the probability of getting the good, that is at least as high as any type that he could pretend to be. Okay? So, for example, if type Si has a subset of the messages of type Ti, that in particular means that type Ti has the maximal evidence, has a message that is the maximal evidence of type Si, and he could imitate type Si. Okay, he could say, I'm type Si, and present the evidence of type Si.
So if EI, SI is contained in the ITI, type Ti can imitate.
Exactly, type Ti can imitate type Si. Okay.
The probability depends only on the process type, not on the message.
Yes, it depends on the what they declare about themselves and the kind of evidence they present. But type Ti could imitate type Si by saying, I am Si, and presenting the maximal evidence of Si. Okay, I need to move on. But basically it says that type Ti should get a payoff, which in this case is just the probability of the good, that is higher or equal to any type that he could imitate.
But you implicitly assume that each type has incentives to reveal full information.
No.
But,
No.
but
No, I'm saying it's an equilibrium strategy.
No, in equilibrium, every type reveals all the
Yeah,
information.
you will not benefit from doing otherwise. Yeah.
Yeah, but then it will work, because without this assumption, the incentive compatibility will look the other way.
I don't know exactly what you have in mind, but let's stick to my assumptions.
Let's imagine you didn't reveal everything in equilibrium. Then
What would happen? What would the mechanism do for
then
you?
the incentive constraints would look different, because in particular, Si might have a message which Ti doesn't have, but Ti could still imitate Si without having to present that message.
Did you answer his question?
Yeah, I was-
Okay. So I'm sorry. I am, by the way, one of the agents in Rubinstein's model, namely bounded rational. so I didn't follow, but if you two are satisfied, so am I. Too caught up with this. Okay. Okay, so now let's talk about this. So we have our optimization problem. The optimization problem characterizes the optimal mechanism that is incentive compatible. Now, incentive compatibility only demands that truthful report and presentation of maximal evidence is best in expectation, okay, given the behavior of the other players. Robust incentive compatibility is something much stronger. It says that no matter how the others are behaving, okay, no matter how the others are behaving, the best thing for me to do is to truthfully report my type and present the maximal evidence, okay? So this is the formal way of putting it, okay? Yes, you see, I could, for every profile of types of the other, every profile of reports of the other agents and profile of pieces of evidence that they may send, okay, I'm better off doing what the mechanism tells me to do, namely declaring truthfully my type and presenting maximal evidence, than doing something else that I could do, namely say that I'm some other type and present the evidence, some piece of evidence of the other type. Okay. Now, why is robust incentive compatibility important for us? Perhaps it's something that's obvious to all of us, and I shouldn't say that. But the reason we call it robust is because it really endows the mechanism with a robustness. The principal doesn't have to worry about the fact that some agent might have actually additional information about other agents, or that some other or that an agent actually has a wrong idea about what other agents are, the way the other agents are going to play. He doesn't need to worry about all this because he knows the agent will still, it would still be optimal for the agent to do what the principal wants him to do, namely to report his type and present maximal evidence. So obviously, if we, in general, if we want robust incentive compatibility, we are imposing more constraints on the problem. So in general, we would get the payoff that the principal can obtain if he insists on robust incentive compatibility is in general, of course, lower. And one of the results says that in the allocation problem and in the other problems I mentioned, that's not the case. You do have an optimal incentive compatible mechanism that is also satisfies this robust incentive compatibility. Okay?
What is stronger than equilibrium dominance practice?
Okay, so let me say a word about that. Again, conceptually, it's the same thing, but maybe I'll give a little example. Yeah, the definition, but I wonder whether looking at the definition is better than just simply telling to yourself, saying who I am, providing maximal evidence is best for me to do, no matter what the other agents say about themselves and no matter what pieces of evidence they present. That's what this definition says. Okay, that's what this definition says. Anyhow, one example that you, I'll try to make it as simple as possible. Let's take the case where there are just two agents, and we're looking at the things from the point of view of agent 1, okay? Say agent 1, to keep things simple, agent 1 actually has just one type, and he has two possible actions, A and B. This is agent 1. Now, agent 2, he has two types. Let's call them T2 and S2. And each one of them is with probability half. Now, I'll be talking in terms of type-dependent messages because really that's the point. The point is that we are in a situation where there are type-dependent messages. So let's try to make it as simple as possible. and say this guy can send those two messages X and Y, and this guy can send the message Z. Okay? Now, what does it mean that A, okay, now suppose the mechanism, okay, depends only on the kind of messages, not the cheap talk reports, but just the messages that the agents present. Okay? So player 1 can present A or can present B, and this is what type 2 could do. Now, what would it mean that A weakly dominates B for player 1? It would mean that A is better than B, yes, better than B, both against, excuse me, the B should be this one. Oh, yes. Both against, no, it's, sorry. Both against the strategy, both against the distribution half X, and both against the distribution half X and half Z, and against the distribution, you know, the alternative strategy that agent 2 might play, which would generate a distribution on messages, which is this one, right? But robust incentive compatibility requires more than that. That is what A weakly dominates B would mean. Okay? That it's A is better than B for each strategy that player 2 plays, right? So player 2 has here just only two strategies, you know, either this type plays X or this type plays Y, okay? So A, and that generates those two distributions on messages, okay? But of course, robust incentive compatibility requires much more. It requires that A is better against any one of these messages with probability 1, okay? And note that it's also stronger than ex post incentive compatibility, because suppose, for example, so it's stronger than the combination of two. Assume, for example, that in the equilibrium T, this guy plays the action X, this guy, of course, must play the action Z. Then ex post incentive compatibility, okay, would say that A is better than B both against the message X with probability 1 and against the message Z with probability 1. But it would miss the fact that A, which robust incentive compatibility requires, that A would be better than B also against the message Y with probability 1. Okay? So this is a simple example where robust incentive compatibility is stronger, not only each one of them separately, but the combination of the two. Okay, but again, conceptually, it's the same thing. Okay? Conceptually, an agent does not need to worry about what the other players are doing. Is that okay, by the way? Or? Mm-hmm.
Another equilibria.
What?
It doesn't rule out that another equilibria are possible.
It doesn't rule out because you have here, you have here equality. No, it doesn't rule that out. You have weak inequalities. Yeah.
And I'm going to present maximal evidence no matter what the others do.
Yeah, no matter what the others do.
So maybe you don't need the normality.
Maybe.
Maybe you don't need the normality.
We don't know. Again, this is something we didn't go into. Okay, we didn't go into that. because we wanted to apply a direct revelation mechanism and focus on that. Okay? So I can't tell you right now how much this assumption can be weakened. Okay, so this is just a formal restatement of what I told you in the beginning, that the result is that there is an optimal incentive compatible mechanism that is deterministic, that satisfies this robust incentive compatibility. And then part B talks about the no need to commitment result. It says that, again, what I told you, that the outcome of this optimal mechanism can actually be implemented in an equilibrium of a game where the agents make cheap talk statements and present evidence, and then the principal acts in an ex post optimal way. And that furthermore, the strategies that the agent use in the equilibrium of this game are the strategy that agent I uses in the equilibrium of this game is an equilibrium strategy in an auxiliary game where it's just him with the principal, okay? Him, the principal trying to match, the set of action for the principal is the real numbers, and the principal is trying to match the value of the agent. Now the quadratic function has this property that if the principal is uncertain, okay, about the type of the agent, then he just plays the expected value with respect to his uncertainty, okay? So that's what the principal does. And the agent has a type-independent preference where he wants the principal to play an action that is high as possible, okay? Now, this connection is not, is intuitive in the sense that on the intuitive level, in both games, agent I is trying to do the same thing, namely to try to convince the principal that he has a high value. Okay? Because that when he has a high value, the principal is more likely to allocate the good to him. Okay. By the way, I should say that the no need to commitment result, saying no need to commitment is a bit misleading. Of course, in the mechanism, the players behave, as we just said, in a very simple way. They just reveal their type and present maximal evidence. In the game, of course, these are not equilibrium strategies. They will have to play mixed strategies, okay? So, yeah, it's, I think, theoretically an interesting result, but if we think in practical terms, we should be believing that agents would be playing those mixed strategies. Okay. Yeah.
Is the optimality of the allocation important behind the robust mechanism for any allocation? So is the result for any optimal allocation I find a robust mechanism, or could I find for any allocation that could be a basic?
The result that we have is for an optimal. Yeah, yeah. Okay, so now let me show you, and it's quite simple, how one could use this last result to compute the solution in where the evidence structure is a die-evidence structure. Okay? Okay, so we have the set of agents. The type of each agent defines a value for the principal from allocating the good for him. And each agent has a die-evidence technology, namely some types can't prove anything, some types can prove everything, or of course remain silent. Okay, now Eddie went with you over the solution of the game. So now look at the, really I want to show you that the result I just told you about is helpful in this case. And I'm going to simply compute the strategies of the agents in an equilibrium of the disclosure game with the principal. Okay, so I'm looking at agent I, and I'm looking at what strategies might he play when he is in his single agent game with the principal. Okay, and here it's especially nice and simple because there would be actually only essentially only one equilibrium strategy, and this follows the logic that Eddie discussed with you yesterday. So let's just go over it quickly. So think of an equilibrium. And the way to solve it, to ask, to start with VI star, which is the expected value in the equilibrium that the principal assigns to the agent if the agent does not present evidence. Okay? So there is such number VI star, and the point is the following, that once we have this VI star, we know how the evidence types are going to behave, right? Because if an evidence type has a value that is below VI star, he would not prove himself. And if he has a value above VI star, he will prove himself. And so VI star has to satisfy that equation, and that has a unique solution. So we have the equilibrium strategy of the agent. Okay, the types who can't present evidence, of course, do not present it. Those who have a value that is lower than VI star want to be pooled with the no evidence types and remain silent, and those who can prove themselves to be above do that. Okay. So now we can go ahead. So now the theorem tells us, and that's the unique equilibrium. So the theorem tells us that must be the strategy of agent I in the multi-agent game. Okay? In the equilibrium of the multi-agent game that gives us the optimal mechanism. That's what the theorem says. Okay? And in this case, it's very simple because there's only one equilibrium strategy in the single agent case. Okay? So those must be the strategies. You know, we know that there is an equilibrium that gives us the optimal mechanism. And the strategies of the agent must be those that we've just, the strategy of each agent I must be the one that we've just talked about. Okay, what does the principal do? The principal, in this equilibrium, the principal responds in an ex post optimal way. What does that mean? So the way to think about it is to say, okay, what does the principal, for each type Ti of agent I, let's denote by Vi hat what the expected value that the principal assigns to type Ti in this equilibrium, and that is given by this formula, right? Because for the known evidence types and the low evidence types, they don't say anything, so he assigns to them the value Vi star, which is the expected value. And of course, those who prove themselves, he assigns to them the right value. Okay? So for each profile of types, he computes. Yeah, okay. So in each profile of types, what's going to happen? We look at those V star values, and he's just going to assign the good to the one who has the highest V star value. Okay. Now there's a simple way to describe this. There's a simple way to describe this. Let's order the star values. Okay, and so assume that the first one has the highest and so forth. So one way to describe, we can describe this mechanism in the following simple way, and we call it a favored agent mechanism, where agent 1 is the favored agent, and there's the threshold is V1 star. What does that mean? It means that if no agent different than 1 proves that he has a value that is higher than V1 star, then the good goes to agent 1. Okay? The good goes to agent 1. Otherwise, we just give it, we look at those who have provided evidence for us, and of course give it to the one who proved himself to be the highest. Okay? So the mechanism takes the optimal mechanism takes a very simple form. Again, there's a certain favored agent and a cutoff. If no other agent proves that he's above that cutoff V1 star, agent 1 gets the good. Otherwise, it's the one who proved himself to be the highest. Okay, now, to our surprise, this has the same structure that we found to be an optimal in a previous paper, which looked at a different model. It looked at the model where there's no evidence, but rather the principal can check the agents at a cost. Okay? So the agents make cheap talk statements, and then the principal decides whether and whom and with what probability he wants to check. But he pays a cost for that. Okay? No evidence, but costly verification. And there you get also an optimal mechanism that has a favored agent structure. Okay? So there's a favored agent and a threshold, such that if no one claims that he's above that threshold, the favored agent gets the good, and otherwise, the one who makes the highest claim is being checked with probability 1, and if found to be truthful, given the good. Okay? So, if I'll have time, I'll talk to you more about. So, at the beginning, we didn't. It wasn't clear to us whether this was just a coincidence or there's something more interesting going on, and it turns out that there is something more interesting going on. And if I'll have time, I'll show you how the costly verification model can actually be translated to a die evidence model. Okay? Now, for us, the neat thing about it was that it also, this connection makes it possible for us to solve an extension of the problem that we looked in the first paper, where there are k units, because it's very easy to extend the solution I just described to you in the die evidence model to the case where you have, instead of 1 unit, k units. Basically you assign the units to the k agents which have the highest v v hat value. Okay. Now, there are two things I would like ideally to do: give you some sort of a proof sketch, and then talk about the relationship between the costly verification model and the die evidence model. Okay? So let's start with the proof sketch. So, okay, first thing we do is okay, the first part of the proof, I will give you an idea, an almost complete proof, as to why we have an optimal mechanism which is deterministic and satisfies this robust incentive compatibility. And the second, I'll kind of sketch the no need to commitment part. Okay, so the first step is to partition the type of each agent according to the probability with which he gets the good. Okay? Now remember, it's a finite model. Okay, so those different alpha i's, there's a certain, I'll return to that point soon. There's a certain minimal epsilon, okay, such that if you look at two different alpha i's, the difference between them is greater than that epsilon. And now look at the partition that on the product space, the product partition, if you wish. Now, a technical lemma that really gives a good mileage, says that there is an optimal mechanism that is measurable with respect to this partition pi. Okay? So you take two profile of types such that for each agent I, the type in the profile T and the type in the profile S get it with the same interim probability, the mechanism treats the two profiles completely the same. Okay, and the argument basically is a simple argument of averaging. Okay, so what I show you here is that looking at it from the point of view of agent I, look at two types of agent I who belong to the same element in the partition of agent I. That is, both the type Si and Si prime receive the good with the same probability. Okay, and what I want to show you is that we can really modify the mechanism so that it remains, the incentive compatibility will be maintained and the expected payoff of the principal will be maintained. But the new modified mechanism will treat the types Si and Si prime precisely in the same way. Okay, that is precisely in the same name. Namely, no matter what is the profile of types of the other players, it gives it with the same probability to. Okay, and what you do is simply you average the probabilities. Okay, you average the probabilities. You give, which is what is written here. If you average those probabilities, where you do that for each profile of types of the other players, step by step, you do that for all of them. So, of course, this doesn't change anything, right? From the point of view of a player that is different than I, you haven't done anything, okay? Because you just, from his point of view, it looks the same. He's just getting that same average. And since the types Si and Si prime started with the same expected probability, this averaging terminates with them having the same probability. Okay? Their probabilities conditional on the profile of the others have been changed, but they don't care. But that doesn't change. That doesn't matter. Okay? That doesn't matter, not for the incentive constraints and not for the objective function. This modification does not change those interim probabilities and therefore do not change the value of the objective function and the incentive constraints. Okay, so we know that we can move to a mechanism, to an optimal mechanism. We can think there is an optimal mechanism that is measurable with respect to this partition pi. Now the next observation is that if you perturb a mechanism a little bit, you start with a measurable mechanism P. Okay, start with a measurable mechanism P, and perturb it a little bit, but keeping it measurable with respect to pi. Okay, you started with something that is measurable with respect, you perturb, change the probability a little bit, but you keep it measurable with respect to pi, then you still have an incentive compatible mechanism. Okay? And the reason is the finiteness of the model, the fact that we have some strictly positive epsilon such that the following property holds. You take two types of any agent I, either they have the same probability or the difference in the probabilities in which they get the good is greater than that epsilon. Okay? So if you would change just a little bit the probabilities, but keep the measurability with respect to pi, then you get, you still get this relationship, that namely, for each agent I, for each two types, if in the original mechanism the probability was higher for type Ti than type Si, then also in the perturbed mechanism, and therefore the incentive constraints don't change. Okay. But then that means that the optimal mechanism must be a ex post optimal conditional on each event pi. What does that mean? It means that, remember, we have an optimal mechanism that is measurable with respect to the partition pi. Take some element in the partition, which I denote by little pi. What the principle does, okay, so the principle takes a single action on this event, okay, and the action he takes must be the one that maximizes his expected payoff given this pi, okay? Must be such, because if it was not, then he could move a little bit in the direction of optimality. He could move a little bit in the direction of optimality. The incentive constraints, because of our previous lemma, would be maintained, okay? Okay, so that tells us quite a lot, right? That tells us basically, this basically brings us almost to the determinism and to robust incentive compatibility, because then what does that say? That says that, you know, when the principle, what is the optimal action for the principle when on such an event? Okay? Okay, so for each agent I, he looks at the expected value for him. You know, he has now a profile, okay, and this guy, say agent I belongs to the element T alpha I, okay? So he assigns to that agent, I mean, since we know that, you know, he acts, he on the event, on the whole event pi, he takes one action. So from his point of view, he says, I'm assigning to agent I the expected value given that he comes from this set, okay? And then I would just give it to the agent who has this highest expected value in this event, right? That's what he would do. That's what he would do. Ask me if there's any. Okay, so that means that, you know, if he gives it to agent I with a probability that is greater than 0, then agent I must be an agent that maximizes this this value. This almost gives us determinism. Well, it certainly gives us determinism if there's, you know, in each such event pi, there's a single agent that is maximizing this VI. And it also gives us a robust incentive compatibility because agent I wants to appear to be the highest have the highest value, no matter what the other agents are doing, right? No matter what the other agents are doing. He wants to put himself in a set to which the principal assigns the highest expected value, okay? And it doesn't matter what the other agents are doing. After all, it's quite intuitive, yeah? but you need to prove that, okay? It's not surprising. Okay. Let me tell you now.
So just
yeah.
quick, this argument is making strong use of finiteness.
Right.
Do you know what happens if you have a continuum text?
I would like to say not yet, but I want to be modest. What does that mean? Locally unique? No, it's just finiteness gives you what you need. Because if there are equalities, they can be dealt with. If there are equalities, they can be dealt. I'm saying the model deals with the possibility that two types are the same, say, in the value that the principal assigns to them or in the evidence. Yeah, but that is in a. Yeah, that's in. Yeah, I simply. Yeah. I define my partition. Yeah. Okay. Let's talk a little bit about no commitment. So first of all, what's the problem we have? Well, the problem we have is that we have a direct revelation mechanism, and we saw that the optimal mechanism is measurable with respect to pi. So it treats different types of agent I in a similar way. But of course, if types are really, maybe I'm saying something that's obvious to everyone. If types are revealing themselves, then the principal has much more information, and of course might want to act in a different way if he's not committed. Okay? And the direct revelation mechanism, he knows exactly which are the types. He gets much more information than he uses in the optimal mechanism, and therefore might want to act in a different way. So it's an issue. Okay, there is also the other issue that although I didn't actually really mentioned it so far, I had to talk about what happens if a type misbehaves and says that he's SI but does not give him the maximal evidence of SI or something of that sort. Well, in a mechanism we have no problem. In the allocation problem, we just, you're misbehaving, you'll get it with probability 0. But that does not apply. Okay, so there's a punishment that applies to all types, as we discussed at the previous occasion. So, but in a game, of course, this has to be taken care of also. So these are the two. This problem is not difficult to deal with, actually. The main issue is the first one. Okay. Okay. So now we really use the single agent games to construct an equilibrium in the following way. This is just a reminder, okay? Because the first step I'm going to do is I'm going to tell you what are the strategies of agents in this auxiliary game between, what is the strategy of agent I in this auxiliary game between agent I and the principal. And this is just a reminder of what it is this game. Okay, so the point is that we can do the following. We start with a game which we call the restricted auxiliary game. Okay? In this game, agent I, okay, we are looking now at agent I, and we are now about to construct an equilibrium strategy in the auxiliary game for that agent, which we will make use of in the multi-agent game. Now, the first step is to look at a game that is a restricted game. In this game, a type in the set a certain element of the partition can only present maximal evidence of types in his event. Okay, so if a type Ti belongs to this set, it can only present maximal evidence of other types that are in that set. Okay? This is a game. It has an equilibrium. And the information that is revealed, what we want to note is that the information that is revealed to the principal in this game is more than what he uses in the mechanism. right? Because in particular, he knows each agent Ti from what set is coming. Okay? Now the main step in the proof, okay? So there's a certain strategy in this game, which is an equilibrium strategy, and the information that the principal has about the agent, when agent I plays this strategy, is more refined than the one he uses in the optimal mechanism. Okay, now the main step is to show, and this I really don't have time to do, that because our starting point was an optimal mechanism, this strategy for agent I is actually an equilibrium strategy also in the unrestricted game. I don't have to worry about agent in a set T alpha I pretending to be an agent in another set. Okay? And the reason we get this magic is that we started with a partition that was defined by an optimal mechanism. Okay? So one could show that if we would benefit from such a move, then the mechanism was not optimal. One could construct a better mechanism. Okay, now once we have this, we are basically done, because now we say the following. Okay, take all these strategies of the agents and let the principal respond in an ex post optimal way with respect to the beliefs that are generated by these strategies of the agents. Okay? So he has a belief about each agent I, and he responds in an ex post optimal way. That is, he gets the reports from the agent, he just looks for the agent which has the maximal expected value given these reports, and he gives the good to him. Now is okay. So now we just need to say the following. First, this is an equilibrium in the multi-agent game without commitment. Principal is responding in an ex post optimal way with respect to his belief. Why are agents? Because again, the interest of the agent in the multi-agent game is similar to his interest in the single-agent game. In both games, he's trying to show to the principal that he has the highest value. Okay? So if he had a deviation, in the multi-agent game, which would have benefited him, it means that he could do something that would make the principal think that he has a higher value. But then he would like to do that also in the single-agent game. Okay? So that's an equilibrium. And finally, because of our first comment, it must achieve the payoff that the principal gets in the optimal mechanism, because the principal has now more information. He acts on more information. So his payoff in this equilibrium cannot be lower, okay? And of course it cannot be higher, because a mechanism always allows us to get a higher payoff. Okay? So that's the structure of the argument.
Something basic I'm missing here. You are reusing phi, which is defined by the probability that the object is granted to the agents. But this is a
Which pi are you talking? No, the pi is a partition.
Yes, it's a partition.
Yes, right. Right.
But the probabilities depend on Q, on the mechanism, where the input are both the types and the evidence.
Right.
So if you change the game, what is the meaning of phi? Isn't phi a construct that is specific to a particular equilibrium in the original game?
Look, pi came from the optimal mechanism, okay? I mean, we're talking about, in the mechanism, I mean, both in the game and in the mechanism, agents make cheap talk comments. Actually, one can show that in the allocation problem, you can dispense with the cheap talk statement, although it's not I mean, but it can be shown, but never mind. In general, he makes a cheap talk statement and presents evidence, okay? Now, that's the difference between the mechanism and the game is just that in the mechanism, the principal pre-commits to what he will do, while in the game, he does an ex post optimal thing. This pi comes from, is endogenous, if you wish. It is defined by the optimal mechanism. It's not part of the elements that define the problem.
Optimal mechanism and particular strategy is that mechanism, right? Which ties specific evidence to each type. Where?
It's defined by the optimal mechanism. It's endogenous. It's not part of the elements that define the problem or the situation. Okay? Okay, this I have to skip. Okay, so let me tell you a little bit about this relationship. So, if not, you're not totally exhausted. So we are switching models. We are now talking about a costly verification model. There's no evidence. Instead, what a principal can do is when he gets a profile of cheap talk reports of the agents, he can decide which to check, whom to check, with which probability to give the object, and so forth. Okay? And the result that we got in this model is, as I told you, it's again that there is an optimal mechanism that is a threshold mechanism. That is, you have a favored agent I and some threshold Vi star, such that if all the agents different than I, for all the agents different than I, this value, you see, you care both about the value for the agent and the cost of checking him. So if this difference is smaller than Vi star, you just give it to agent I with probability 1. And otherwise, you give it to the agent who has this highest value. Okay? You look at, okay, so you're not giving it to the agent who has the highest value, you're giving it to the agent who has the highest value minus cost. Okay, you have an optimal mechanism that has this structure. Okay. Now, I need to speed up a little bit. Now, in this model, first of all, a mechanism could be something rather involved, right? You could get cheap talk reports. Then you could randomly decide to check someone. You check him, you find who he is. You might want to check someone else. Along the way, with some probability, you might want to give the good to someone, and so forth. But arguments that are similar to the revelation principle say that you can basically restrict attention to mechanism where you when you get the cheap talk profile of reports, you with some probability select an agent, with some probability decide whether to check him or not. If he's being checked and found to be truthful, you give it to him. If he's checked and found out to be lying, you don't give it to him. If you selected him and decided not to check him, you just give it to him. Okay? So you can restrict attention to this class of mechanisms.
You say you're choosing an agent at random.
Right. As a function of the cheap talk reports. I might. I mean, in the end, I don't. But, we start with maybe choosing at random, selecting an agent at random. then deciding at random whether we check him or not. Okay? The simple argument that if you check him and he's found to be truthful, you give it to him. If he's lying, you don't give it to him. Okay? And if you selected him and decided not to check him, you give it to him. Okay? You can restrict attention to those mechanisms. So now, okay, I'll try to speed up. So PIT is the probability you give it to you select. Actually, PIT is not just a select. PIT is the probability you're going to give it to agent I in the profile T, and QIT is the probability you're going to check him in the profile T. And then again, you want to look at those interim probabilities. And then your problem is this problem. Okay? You see, if you take the type Ti, then this is the probability you're giving it to him. Okay? So it gives you this benefit. And this is the probability you're checking him. You're incurring this cost. What are the incentive constraints? The incentive constraints simply say that if I'm type Ti, if I report truthfully, I'll get it with this probability. If I would pretend to be announce myself as type Ti prime, what is the probability I'm going to get it? It's just the probability that type Ti prime gets it minus the probability that type Ti prime is checked. Okay. Now, I'm beginning to run out of time. So there are certain observations that one can make on this problem, okay, which are on the slides. For example, it's not difficult to show that the probabilities are monotonic in the values. That's intuitive. And therefore, if we think of type Ti0 as the one who has the smallest value, then he's going, in an optimal mechanism, he's going to get it with the smallest probability. So we can actually translate our problem to this problem, right? The type Ti0 who has the lowest value is getting it with the lowest probability. And then we just, given that, we just need to check that he doesn't cheat, okay? Because if he doesn't want to cheat, no one else wants to cheat, because everyone else is getting it with a higher probability, okay? So So we just need to worry that the type who, the low type, doesn't benefit from cheating, okay? And then you look at this constraint, you say, well, it has to hold with equality, right? Because you're paying for checking, why overcheck, okay? But that means that you can derive the probability of checking from the probability of allocations, okay? So you can reduce that problem to the problem of finding the probabilities of allocation. Now, you play with this problem a little bit more. You get, some algebra brings you to this. And now the point is, because I need to finish in a few minutes. Now the point is this. Now we are really just 2 steps from reducing it to a problem that is a die-evidence problem. Okay. The first step is to say, right now my objective looks like this. But if I redefine values, if I define, never mind the details, I'm just defining adjusted values, and now never mind why I do it this way. The point is that when I look at adjusted values, I can define my problem in these terms. Okay? think of it as this problem, as the problem of maximizing this expression, which is giving the good, to an agent where the benefit the principle derives from giving the good to agent I of type Ti is this adjusted value. But now if you look at this problem, you say, well, that's exactly a die evidence problem in the following sense, okay? And you can think of it as a die. You can think of it as an optimization problem that gives you the optimal mechanism in a die evidence model where the value from assigning it to type Ti is just this adjusted value, and where the evidence structure, what about the incentive constraints? The evidence structure is one where the only type who does not have evidence is the type Ti0, and all the other types have evidence. If that's the model you're looking at, then those are exactly your incentive constraints. Because what do the incentive constraints say in this case? They just say an evidence type would not benefit from mimicking the no evidence type. Right? That's the only thing it can do. So that's actually the problem, the mathematical problem that defines the optimal mechanism for a die evidence model where those are the values and where type Ti0 is the only type that has no evidence. Okay, done. Thank you.